Hi again, everybody. Welcome back. Example 1016 is another example of accounting for all the energy at various different points as the system moves or kind of changes its the types of energy that it has at different points. Now, you'll notice right here that there are no values, that there are no numerical values, I should say, but we have everything in general terms. We have a disk with radius r. It's got an initial angular velocity of omega, an initial linear velocity of v, and I guess a block right here of mass m. So what's happening is initially this system is in motion. Like think of it as being like a ball thrown up in the air. Okay, so initially it has velocity, but at the top it comes to rest because all that kinetic energy that it initially had gets turned into potential energy. Okay, so right here, this block is moving up and this wheel is rotating. All right, this solid wheel is rotating right here. So the question is going to be, to what height does the block rise before coming to rest? So the h is what we want to solve for right there. It looks like an n, doesn't it? It's an h. H is what? So it's going to be h in terms of all the other things. And I can tell right away I'm going to have to shrink this down a little bit. I may need to shrink it down even more a little bit later on. But now, since we're dealing only with gravity right here, it's the only force that is slowing the system down, or at least changing the energy forms from one type to another, is gravity, then that means that all energy is conserved, because gravity is a conservative force. So that means we can say that the total energy initial of the system is going to have to be equal to total energy final of the system right here. Okay, so by the way, let me kind of redraw in here. It's this h starting from here and going up to here that we're trying to solve for. All right, so if this is moving up and the wheel's rotating right here, how high up will it actually go before stopping at a maximum height? What is that height we want to solve for? All right, well, let's start by writing in the kinds of energy that the system has at the different points. Okay, so initially, this block right here is moving upwards. It has a mass and it's got an upwards linear velocity, and so therefore, it's got, it's a terrible K, it's got a linear kinetic energy of B, the block. Okay, that's what the B stands for. That's initially what it has, but also we have this wheel right here that is rotating, and therefore it has rotational kinetic energy of the wheel right there. And that's going to be what that has, that's going to be what the block has right there. So the block doesn't have any height, therefore it has potential energy of the block equals 0, right? But let's compare it now to the final condition of the system right here. All right, the final condition of the system, it has no rotational kinetic energy, right? The wheel has stopped. It has no linear kinetic energy. The block has stopped, but it does have gravitational potential energy, and of course that is mgh. M being this m of the block right there. All right, so the energy that the rotating wheel and the moving block had all went into raising this block up to a certain height. We want to find out what that height is. Okay, so let's take those values and write them down below. So the initial energy that the system has is rotational energy of the wheel plus linear kinetic energy of the block, and that's going to be, and I'm spreading this out for reasons you'll see in just a minute, equals the final gravitational potential energy, which is UG. All right, I can see right now I'm going to have to shrink this down even more so I have some more space. Hope that doesn't bother anybody too much. All right, now the reason I left all that space right there is because we're going to have to expand all these out, right? Let's write out rotational kinetic energy of the wheel. Let's write out linear kinetic energy of the block. Well, the wheel, that's going to be 1/2 times I times our angular velocity squared, right? Plus linear kinetic energy of the block. That's that right there. So that's going to be, we know what that is, 1/2 mv squared equals, what's our gravitational potential energy? Well, it's going to be mgh, right? And hey, there's our h. There's what we're solving for. So if we can turn all this other stuff around and solve for h, that's going to be our final answer. Okay? Well, let's see if we can get some things to, if not cancel out, at least to sort of factor. Now we have this this v right here and this omega right here. We know that omega can be stated, the angular velocity can be stated in terms of v, right? We said before, earlier in the chapter, that our angular velocity is linear velocity over radius. So if that is squared, then that means it's going to equal linear velocity over radius squared. So let's substitute that in for omega squared right there. Okay, so that's going to be 1/2 times our I didn't make that I very big, did I? 1/2 times our I, our moment of inertia, times velocity squared over radius squared, plus 1/2 mass times velocity squared equals mg h. Now again, this m, this little m here and here is the same m, but we can't cancel it out because there's no m over here on this side, at least not yet. Okay, so here's the point where we're going to have to kind of look back and see what we can make out of this right here. All right, now if you recall, well, first of all, the initial energy of the system is all kinetic, right? It's kinetic rotational and kinetic linear. And a few slides back, let's jump back, I don't know, 1, 2, 3, 4 pages or 4 slides in our notes back. We had two definitions of kinetic energy. Well, it's not two definitions, but it's two versions of the same thing. This is linear kinetic energy, and this is rotational right here. But if we factor out a 1/2 mv squared from this, so we pull out 1/2 mv squared out of this, that becomes 1, right? If we pull out 1/2 mv squared here, then, well, the half goes away, and since this, and we already wrote this, is v squared over r, the v squared comes out, but the r squared stays in the denominator. Now, the only thing that doesn't, isn't 1/2 mv squared right here is the m. There's no m in here, so that means the m has to go into the denominator. All right? So this is really just a restating of this as if we factored out 1/2 mv squared. So let's do that in our problem right now. All right, so it's going to be 1/2 m, now that's lowercase m, v squared. So that comes out of this whole thing. So we've got the 1/2 and the v squared, but the m is going to have to go into the denominator. So it's going to be I times I over v squared over r. I over mv squared. I over m, I can't even think straight. I know what I want to write, I'm not saying it. I over mr squared. That's what we said happens right, let me flip back here, right here, right? Yes, so it's I over mr squared. And if we go back to the problem, plus 1, because, well, this whole thing comes out, that's 1/2 mv squared, so that comes up out front. So this whole thing has to be in brackets right there, all right? And that's going to be equal to mgh. All right, in fact, let me spread that out, expand that out a little bit more so it kind of lines up better, equals mgh. There we go. Okay, so we're solving for h. And now we can actually get rid of that mass right there. Since that's the same mass on both sides, that the mass of the block, that and that cancels out. But we can't really do anything with this mass in the denominator right there because it's being added to this 1. So that has to stay in the denominator. But if we do our kind of final algebra to get everything away from the h right here, we're going to have to take this g and divide it down. So it'll really become sort of in the denominator down here under 1/2 v squared. So this is going to become 1/2, or you might say v squared over 2. So v squared over 2, and then of course we divide down this g, so that goes down with the 2 as well. So it's going to be 2g times I over mr squared. That's what I had so much trouble with spitting out a few minutes ago. Plus 1, which is a very bad 1, plus 1, there we go, equals h. All right, that's our height, and that's actually our final answer. Now, it may look ugly, but what it tells us is this. Depending on what the moment of inertia of that rotating disk is right there, that will determine how much higher up it goes. Think about this for a second. If a block only had, let's draw this in green for a second. If the block only had linear kinetic energy, if the block only had linear kinetic energy going up, then that means that the height that it would go up to, or that the gravitational potential energy that it would gain, would only be a function of whatever that is right there. But the system has not only linear kinetic energy, but also rotational kinetic energy. So the fact that not only is the block moving up, but also the wheel is rotating around like that, the rotational inertia, or the rotational kinetic energy of the wheel, actually makes the block rise to a higher height than it normally would have if you had simply thrown the block up in the air. Now this this right here, I'll keep it in green. That moment of inertia of the disk, or of the wheel right there. Well, we know that the moment of inertia of a solid disk is 1/2 mr squared. Now that m is the mass of the disk, not of this other mass, which is of the block right there. All right, but depending on how the disk is shaped, maybe it's not a disk, but it's got maybe some spokes and most of the mass is around the edge right there. Now, that could be, I'm just putting a slash here, it's not a dividing line. It could be mr squared, not 1/2 mr squared, but mr squared if it was like mostly just an empty wheel with spokes. The point here is that depending on what the moment of inertia of this object is, or what the shape of the object is, or how the mass is distributed, that will make this, in the brackets right here, greater or lesser. All right, so if it's 1/2 mr squared, all right, well, the r squared goes away, and if you add that to 1, that makes your height something, all right, some value. But if it's simply mr squared, if we put that in, if it's an empty wheel, or just mostly a wheel with mass around the edges and just some spokes holding the mass out there, then that would make our height even greater. So the point here is that depending on what this moment of inertia is of this wheel, that'll determine how much energy the system has, and it'll make the block raise up any higher, because the wheel's going to want to continue to spin and spin and spin and spin until its rotational kinetic energy is finally at 0. So this is, like I said, sort of a kind of ugly equation right there for our height. But it does tell us that as we change the moment of inertia of that wheel, that will determine how much higher up it goes than if you had simply thrown it up in the air, or if you had a wheel that was had the mass distributed different ways. So that's it for example 1016. In the next one, we should be able to plug some values in and actually have some calculating to do, but we've been dealing mostly just with general terms right now, because we've been really just applying conservation of energy. All right, so when we got to this point, we basically had it solved. We just had to do some algebra to solve for our height, and there it is. So thanks for following along. Make sure if you have any questions to ask me, and I'll see you on the next one.